Good morning, welcome back to Math 365 PDE. So nice to see you. Sorry to interrupt your conversation. We have to do class, that's right. We should take a break from chatting and do class for a little while. Just a little while. If you have access to Zoom, I'd like to show you some Zoom things today because I want to finish up this problem. And it does have a numeric component to it. That wasn't a weird equation. That was just like tangent of x equals like 1 over 1 plus x squared times constant. It's not bad. It's not bad. But we'll talk about that. While you're getting that set up, I'll briefly reintroduce you to where we were and hopefully not take too long to get back into it. But we had looked at separation of variables for this heat equation problem. We found g sub n equals e to the minus lambda n times t, lambda n to be determined. This was our time function. Our space function was y sub n is a cosine root lambda n times x plus b sine root lambda n times x with perhaps a condition on the coefficients to be determined, and once again, lambda n to be determined. And this is with the caveat that this is true if lambda n is a positive number. If it's not a positive number, then you would either use a linear function, which we ruled out, so lambda is not 0, or if it's negative, we could have exponential function, which we didn't rule out. But let's talk about that. We also found that b times root lambda equals a naught times a, so that b equals a naught over root lambda times a. And if you substitute, so I'll write that down. So we found that b equals a naught over root, calling it root lambda n because eventually the lambdas will depend on n. But we found this equation from our initial conditions that permit me not to write everything down again. And if you make that simple substitution, then you'll get a times cosine root lambda n plus a naught over root lambda n sine root lambda n times x. And now you get, so you can have any constant times g sub n, you can have any constant times y sub n. Eventually we'll multiply these together and add them up, and at that time I'll add in the constants, but for now I'll just take a equals 1. So you understand that when I'm finding the final solution at the end, I'll introduce the constants back when I'm taking linear combinations. But I just want to point out, it is wrong to say a equals 1 and b equals 1. What you do is you get the general form of a solution first, you use your initial conditions, and then once you're here that it's just constant times that, then it's okay to say, look, I'll just reintroduce one constant when I'm multiplying them together. Alternatively, you would really need 2 different constants when you're multiplying them together, and you'd still need to figure out this relationship, but we figured it out a little bit early. So not to belabor that too much. And something else came out of the initial condition, and I'll just write back what I had on the board last time. Thank goodness for the video, because I could go back and look and verify that this was what it was. Tangent of root lambda equals minus a naught plus a1 over a naught times a1 over root lambda minus root lambda. And you'll see that the places where these two graphs intersect, it's going to be a discrete set of places. And so you'll be labeling them lambda 1, lambda 2, lambda 3. And that gives you your lambda n. So you can solve this numerically so long as you've got a naught and a1 specified. Remember these conditions: a naught less than 0, a1 bigger than 0, and what? A naught plus a1 bigger than a naught times a1, bigger than the negative of that product. You can clean up the algebra on this a little bit. So you could multiply by root lambda over root lambda to get, root lambda plus u on top, and then constant minus lambda. Just point that out. And okay, so first things first. We wanted to make some argument with Rayleigh quotient that said that lambda had to be bigger than or equal to 0. We ruled out equal to 0. And if we could use Rayleigh quotient to say that it's bigger than or equal to 0, then that's what Logan calls an energy argument. Then we'd be good. Remember, this was like p times y prime evaluated from 0 to 1. Your space domain went from 0 to 1. In this case, p was equal to 1. So you were just left with this. We did some algebra and found out that, I think I remember what we found out, but maybe I wrote it down. We found out that this was, I believe we found out after plugging in initial conditions, this was a naught times y of 0 squared plus a1 times y of 1 squared. And like we had some remark that said, look, if y1 squared is bigger than or equal to y0 squared, then you can use this equation to show you that lambda is bigger than or equal to 0. On the other hand, what happens if that's not true? We just got this equation that said this was less than or equal to some positive number, which is true, but not helpful. I'll explain a little bit more my perspective on this. I've got a little Desmos illustration, but also, I thought about this for a moment and I said, look, well, like if you make vector A naught, A1, and if you make vector Y y0 squared, y1 squared, then this is really the dot product of A and Y, isn't it? And this is something like length of A times length of Y times cosine of the interior angle between them. And so it got me thinking, because it got me thinking, am I really just missing an argument, or is it just not true that the Rayleigh quotient says that this has to be positive? So we really need to look at the angle between these two vectors, I would say. And you might think that's completely hopeless, but it's not completely hopeless, because these coordinates are like non-negative. So this vector lies in the first quadrant, right? Like y has to be somewhere here, because both its coordinates are bigger than or equal to 0. And this vector also has a condition coming from this constraint. So if you graph like x plus y bigger than minus xy, and you add these conditions that x is left, left of 0 and that y is bigger than 0, you'll see this little sliver of the plane where vector A can lie. And so that's what I'll show you on Desmos right now. Okay, is that visible to you on Desmos? I've got some other things on the left too. We'll get to that later. But so here I just graphed the inequality that came from the condition, and you see that x for A naught and y for A1. And you can see that the condition that x or A naught is less than 0 means you're like over here, this region I'm mousing over, and also you're asking that y is bigger than 0, and you satisfy this inequality. So you've got this region bounded by the dotted line and the x-axis and the y-axis. So you're in this little region. That's where vector A can live. And I'll sort of indicate it here. So here's vector A. And you've basically got, like, in terms of how big can this angle get, I mean, you're basically looking at the tangent line here. And it's just whatever that angle theta is, right? Because I'm allowed to, I mean, the vector would get shorter and shorter, but I'm allowed to kind of tweak this over, as far as I want to sort of get closer and closer to the angle represented by this tangent line. And maybe I didn't draw that tangent line super accurately, but it's more right that it's maybe over there. So the angle that I've kind of drawn between y and this tangent line, or certainly the angle that I've drawn between y and A, looks like it's less than pi over 2. Right, here's cosine theta, right? So this is my point, that like if theta is between 0 and pi over 2, then that's what you want, because then this thing is actually going to be positive. And this was actually minus p times y prime. And after calculating that out, this is what we got. So this is the thing that you want to be positive. This is sort of correctly calculated. So is this always going to be positive? That really boils down to whether or not theta is always going to be between 0 and pi over 2, I think. So it's basically telling you, if you're online, you can't really see the board, but all I did was redraw the picture that's already there on your screen, picture of the region. So I'll stop sharing so you can see it. And so does Rayleigh quotient say that lambda has to be positive? No, because you could, if you're allowed to choose y0 and y1, then you could choose these numbers so small that this vector y is very close to the x-axis, right? So close that the angle determined by y and A would then be bigger than pi over 2. So depending on, like if you were fixing these constants first that satisfied this condition, so you had to be in that region. And if you were allowed to pick y0 and y1, then you could pick them in such a way to make this product less than 0. So that's definitely possible. It's definitely possible. It's still true that lambda has to be positive, but not because of this argument. So Rayleigh quotient is answering for you the question, like, does the structure of the equation imply that lambda has to be positive? And in this case, the answer is no. But you know more than just y0 and y1. These aren't arbitrary numbers coming out of nothing. Y0 and y1 are inputs or endpoints of a function that solves a differential equation. So if lambda is negative, then y would not have this form. Y would be a sum of exponentials. And then with that new information, is it still true that this sum could be less than 0? And I say no. In other words, you just have to do a usual case argument.
So if we assume that lambda is negative, and through that we assume we get exponential answers, that the form of y, the y vector there prevents us from getting negative lambda values?
No. If lambda is negative, then y sub n is like a times e to the minus lambda times t plus b times e to the root lambda times t. And then just play with your initial conditions and make a contradiction. So indirectly, it'll be true that these, that this won't be able to be 0 in that case. But it won't come from this equation.
Like that entire term won't be able to be 0?
What that entire term is what?
A naught y0 squared plus a1 y1 squared.
Yeah, what I'm saying is that if it's true that y has this formula, and I don't want to work this out because it's not illustrative. This is the solution in case lambda is negative. If that's true, with the initial conditions given, then this can't be negative. That's what I'm telling you. But you don't have this information in the Rayleigh quotient. That's what I'm saying. So the Rayleigh quotient is not the same thing as solving the equation and using a case-by-case argument.
I don't get why that solution doesn't let us get a negative value for cosine.
But it's quite similar to arguments you've done before, right? And so, I mean, you'd have to argue that way. Like you've done in a previous homework. So if you've got this function, well, I'm not saying it's completely obvious, but like I'm saying, if you've got this function and the initial conditions, then you could argue that a and b must be 0, contradicting the fact that y is an eigenfunction and can't be the 0 solution. But that's what you do. And because of that argument, it will then be true that this is not negative. But it's not like you're seeing that directly. I'm just saying that if you were permitted to choose y0 squared and y1 squared however you liked, you could just choose them both very small. Yeah, but you're not permitted to do that because they have to be inputs to a function of that form. Yeah, that's what I'm saying. But I would also prefer not to go into that. That's not, I don't think that's what you need from me right now on this day, before the test on Friday. That's what I'm asserting to you. So I'd like to not go into it. But I think it's interesting to show you what the Rayleigh quotient does and does not describe. In the argument we had last time, we said, like, what if y1 is bigger than then why not? Or like, what if y1 squared is bigger than or equal to y naught squared? And that's like saying, what if your y vector lied in this region? And your a vector was over there. And then in that case, that means theta has to be less than pi over 2, so you're good. Like, and we saw that. And then the other question was, well, what if you're in the other situation? Like, what if you're in the other part? And it was left unknown to us at that time whether we were just making a mistake or whether it might be true that you could rearrange the inequality.
So the
But no,
question itself doesn't exclude the possibility of a negative value. Inspection of the form of the equation does.
yeah, that's right. Right. The Rayleigh quotient itself doesn't preclude the possibility of negative lambda. So it wasn't like we were just missing some argument there. And that's the thing that I think is interesting. And that's what I wanted to show you.
But that's only for this specific case, right?
Yeah, it's only for this specific question. That's correct. That's correct. So, and there are questions in the book where the author says, use an energy argument to show the eigenvalue has to be positive. So it's like he's written questions specifically to allow you to get a nice answer. But for some of the other questions where you might just try and see what happens, then you can and do get into the situation where the energy argument or the Rayleigh quotient doesn't give you information. It's kind of like, like you've got the ratio test from calculus 2. Most of the time it gives you no information, but we still teach it. Okay, moving on. I want to go forth and find lambda n. So this maybe hope gives you some comfort in that we could really actually choose cosines and sines. And so this I need to go back to Desmos because you have to do this numerically. So I'll take away the other thing. And now I will highlight the the right-hand side of the equation. So the instructions in the book said something like take A naught equals -1/4 and A1 equals 1/4. And so that's what I did. And I wrote x for root lambda. So we're searching for x, and when we find x, that's root lambda. And you'll see I did this multiplication trick just to simplify it. So I got 3.75 times root lambda divided by -1 minus root lambda squared. And then I cancel out a negative sign. And then you want to compare this to tangent root lambda or tangent x. And so at the places where these things intersect, that's your eigenvalues. Now, because I did this trick of multiplying by x over x, that's an indeterminate form. So yeah, it produced this kind of like fake zero solution. But the first real solution to the problem is this 1.08. And so 1.08 squared would be lambda 1. And 1.08 would play the role of root lambda, or root lambda 1. The next intersection occurs at x equals 3.878. So lambda 2 is 3.878 squared. And the next one occurs at 6.779 or thereabouts. And so the square of that is lambda 3. And I stopped there. I just did the first 3. No, actually, I did one more. The next one is 9.787. So you can see this sequence of eigenvalues marching off towards infinity. You do 1.1664, 15.038, 45.954, so on and forth. And then 95.785, that's the first 1, 2, 3, 4. lambdas. And so when I then write down the solution that I write down has to be y sub n times g sub n. And I'm adding them up. So I'm getting from separation of variables that this is the form of u, and so this is going to be, I'll write the g sub n first, it's going to be e to the minus lambda n times t times, well, maybe constant times e to the minus lambda n times t, and then times cosine root lambda n times x plus a naught over, and a naught, well, yeah, I'll just leave it as a naught over root lambda n times sine root lambda n times x. So this is your solution. So this is your solution, and you need a formula for these coefficients c sub n. So notice, like, if I had kept some constant here, and if I had kept a sub n there, they would multiply together and become constant cn. So I didn't lose anything by not including the constants here. It's just to avoid like lots of extra notation, just adding the constant in. I need to find c sub n. And when I find c sub n, I want to do linear algebra. I clearly don't have some classical Fourier series formula to give me c sub n. So when you're finding c sub n, how do you do it? What do you take the L2 inner product against? Do you want to use sine root lambda over x or cosine root lambda n over x? Or you know, both of them, or a distance or a difference? What about this constant? The truth is that Sturm-Liouville theory says that this y sub n, this was the solution to L of y sub n equals minus lambda n times y sub n, where L was minus, you know, p y prime plus q of y. And in our situation, p was 1, q was 0. And Sturm-Liouville theory says that it's these y sub n's that are a complete orthogonal system. So you're not using cosine root lambda n times x. You're using y sub n. You're using this function. So your general theory tells you that if you take the L2 inner product, y sub n and y sub m, with these two being different, then the answer will be 0. I invite you to check that out with like computer algebra system or whatever. I'm not going to. I'm going to use the theorem, which says that it is legitimate to use this as like a basis of solutions. But this allows me to compute c sub n, right? Because I can now take y sub n, take the inner product with u, x, t, and that's going to be equal to, well, I guess first of all, I should say, as we know, that when t equals 0, we've got this initial condition that ux 0 is equal to f of x. So this is the substitution that I'll make. So figure out the coefficient c sub n, plug in t equals 0, obtain f of x, and then take f of x inner product with y sub n. And that's going to be now the inner product with cn y sub n. I'll index it from, m goes from 1 to infinity. right? When t equals 0, this becomes 1, and this is Cn times y sub n. Just changing the index to m to infinity, not to get confused with that one. And by orthogonality, this becomes C sub n times yn, L2 inner products with itself. And so this is the formula you already know. We've seen it 1,000 times. So this is L2 inner product f y sub n over y sub n, y sub n. But the trick is actually writing it out and evaluating it, right? So this L2 inner product of f with y sub n, x goes from 0 to 1. So you've got f times this whole thing. Dx, and then divided by this thing squared. That's your formula for C sub n. As soon as you pick A naught, and as soon as you find a value for root lambda n, then you can plug them in, and I would not try to work out this quotient symbolically. I would just use a numerical solver. And we need to find the first few terms, right? And that's exactly what I did. And you're welcome, by the way, because this is kind of like, it is kind of tedious, but it's a little rewarding, I suppose. So here I'll go back and share my results with you on the Zoom call if you want to see them. And so you can see here's my root lambda 1, 2, 3, and 4, and my lambda 1, 2, 3, and 4, as we discussed. I actually just typed in this quotient. And you can see that I replaced A naught with negative 0.25. I left constant A to take the role of square root lambda n. The textbook asks us to please use f of x equals x times 1 minus x as the initial function. So you can see me making that replacement. And then you can see the last value for A that I plugged in was 6.779. So that's going to be like this C3. So the value of C3 is negative 0.07070543, so on and so forth. And I went ahead, I'll show you the graph in a moment. I went ahead and just typed all of this in out to 3 terms. So the first term is C1. So C1 means plug in 1.08 for A. And you can see the quotient gets calculated to 0.2205, whatever, which I rounded to 0.221. And I've got e to the minus lambda n. So that's e to the minus 1.08 squared times t times cosine 1.08x minus, 0.25 over 1.08 sine of that. So that's correctly entered. The next one, what's this coefficient C2? I have to plug in 3.878.
Is the 1.16 just 1.08 squared?
Yeah, you can see that here. Right. That's correct. So finding now coefficient C1, I get negative 0.084. So you see the coefficient's kind of rapidly decreasing. And then you'll see the second term. There's that coefficient e to the minus 15t. So again, the damping is starting to get huge. Minus 15 was the square of 3.878, rounded, because I don't think that the extra hundredth of a point really matters. And then you can see me entering it in to yn. Finally, the third term, Cn was sorry, Cn takes 6.779 for root lambda. And you'll see that's what I had at the beginning, negative 0.07. And negative 0.071 I probably used. And yeah, you'll see there's my Cn, the negative 0.071. And yeah, once again, these lambdas are getting really big really fast. So this term is very small. I'm multiplying it by e to the minus 46t. So after that third term, I thought, well, negative 46 is big enough that I'm not going to add the fourth term onto it. But there you can see everything that I've added. And the other thing that I'll point out as I take away these other graphs, the other thing that I'll point out is we also had this initial condition. I wanted to include enough terms that my initial condition was actually reasonably well approximated by its Fourier series, because otherwise we're not even doing anything. So since this only goes from x equals 0 to x equals 1, that's the domain restriction I put there. So there's the graph of x times 1 minus x. It's no big deal. And so here's the graph of what happens when you plug in t equals 0. So in other words, here's the graph of the first three terms of the Fourier series. So this is like C1 times y1 plus C2 times, just so you're clear what I'm doing, it's y2 plus C3 times y3. So this is the thing that's supposed to become f of x in the limit, right? With the y1, the y2, the y3 being cosine root lambda 1x minus a naught over root lambda sine root lambda 1 times x, so on and so forth. So it's those yn's that are the orthogonal system. And actually, yeah, they're at time 0. That's right. So you can see it's just the e to the t's become 1. And so here's my C1 times y1, C2 times y2, and C3 times y3. So is it a good enough approximation? Use your judgment. Let's see. Thank you for the the drum rolls. And look at that. It's pretty good, you know?
That's close.
It's actually kind of nice to look at it without the periodicity, to just, you know, see it on the interval that you're concerned about. And you can see here at these endpoints, we've got a little bit of a problem, but, or like there's still not like super close, but, you know, I could add a fourth term or a fifth term, but I thought that was close enough with just 3 terms. And then the final thing that the problem asks for you to do is to say, show me some time slices. And we can actually make a movie, because you can make t be the slider and you can see the time slices. And so I've got it set to t equals 0. Here's the full solution at t equals 0. And of course, full solution is of course equal to the Fourier approximation. So that's good, that scans. It's my like reality check. And as t increases, you'll see the you'll see it flatten out. So this, yeah, so let's talk for a moment about what this equation is. So this is a heat equation. The green line is the initial temperature profile, right? Starting at 0 at the endpoints and increasing temperature as the rod goes from 0 to 1. The red line is the initial temperature profile from our approximate solution. So it's not exactly right, but it's, it's the approximate solution. And this is a heat equation that has radiation and absorption. So we can talk about those. You don't want to, but so those initial conditions with the A0 and the A1, there's a request not to talk about it too much, but if you look at the derivative of U with respect to x. It's like, you can see that your rate of change is like positive. It's picking up heat at x equals 0. It's negative, it's giving away heat at t equals 1. So as you're looking at this approximation, you do expect it to kind of settle down to 0. That's like the damping phenomenon, but you also should hope that you can see the absorption at the left endpoint and the radiation at the right endpoint. Okay, so fine. Let's watch the movie. So this is just 4 seconds of time, but I'm incrementing it by 100th of a second. Okay, here we go. And you can see how we're like picking up heat here, we're losing it there, but we're otherwise flattening out. And you know that stationary solutions to this are linear because, you know, if the time part is 0, you just get y double prime equals 0, which is a straight line. So it's heading towards its steady state, which is a straight line, but it's doing it in such a way that it's absorbing and radiating. And at this point, you know, we're kind of just watching a line fall toward the origin. It's like it's still going, but yeah, happened a lot quicker than you might think. And this is with time slowed down. Yeah, we're still only 3.5 seconds in. So like if I stop this and change it to a step size of like a half.
You put 2.
Oh, 2 decimal points. And then if I go back to t equals 0. So if you watch it like in a speed that's closer to real time, then this is what you see. Well, yeah, and you'd see it go by really quickly if I guess the computer could handle it. Yeah, Desmos is thinking, but I have to preload it. Actually, no, I've got it set to go slow, so that's my fault. Let's take it to half speed. So the speed goes from like 0.01 to 2. So now you can see it just goes away.
It just goes away.
Yeah. Just like a Berkshire winter. So, yeah, any questions or comments on that? So that was just a diversion to, yeah, do one of these, you know, book problems, homework problem. It's an advertisement for Sturm-Liouville theory. Like, it does work. The y-ends that you get don't have to only be cosine or sine. It does give you an orthogonal system. You can use it to approximate the function. And we've seen that here. And the equation did behave in a manner like we wanted it to. Okay, cool. So I know that was a lot of time spent, but I hope that was kind of worth it to look at. And in the remaining minutes, I just want to make sure we're good with some problems that are in my mind that I might ask you on Friday. So what if I give you a question like this? I say, consider this consider this function. defined from x equals 0 to x equals 1. And this is just y equals f of x equals x, but on this interval. And so I can ask you some questions, like I can say, like, to what function does the Fourier sine series and cosine series converge? And maybe I have to think a little bit harder about how to write the question, because you have to do a little bit of work to make sense of the Fourier sine series. So you need to think about, like, perhaps extending this function. But I don't mind, I guess, asking that of you as part of the problem, perhaps. And justify your answer. So I want you to take a few moments and see if you can draw pictures of the function that the corresponding Fourier sine series and cosine series converge to. Yeah. Yeah, that's good. Yeah, so I'll step in and maybe make some comments. Like, I guess when thinking about sine series and cosine series, the Fourier series will be a 2L periodic function. And I'm thinking of this as like 0 to L. And so to get the sine series, to get a proper sine series, I'm thinking about taking the odd extension of this function from negative L to L, and then extending it by periodicity. So the odd extension should look like that, right? And I think it's kind of nice to draw a period on either side. So maybe you're just looking at some sawtooth like that, or it's not a sawtooth, but and then what does the Fourier sine series converge to? Well, this is a function that is piecewise smooth, and you have to say that. So it's it's smoothly differentiable on each interval, except at these finite, jump discontinuities or discrete collection of jump discontinuities. And so at that point, you converge to the average of the left and right limits. So here's a picture of the function that the sine series converges to. Whereas for the cosine series, you would want to take now the even extension. Which would look something like that. So even extension of this function looks like so with these holes sort of not defined. But then when you take the cosine series, then the holes will be filled in. Again, because it's piecewise smooth and these limits are the same, so their average is the same. So the Fourier cosine series doesn't care that you deleted a few points. It will fill them in for you and converge to this sawtooth function. Yeah.
Do all three of the convergence theorems you gave us apply in this situation? Like f prime. Oh no, never mind. Except it's not continuous.
Right, the sine series doesn't apply to this one. It won't converge. It won't be able to converge uniformly because of the jump discontinuities. But it will converge pointwise.
And then is it an L2 function?
All of these are L2 functions.
So then it also converges in the mean square sense?
Yeah. I mean, they're L2 functions on their domain from minus L to L. If you integrate over the whole real line, of course, they don't converge, but that's what is meant. If you can just integrate the function from over one period. And it's something you can actually check, right? Like the square of this function, I mean, it's a piecewise function, but it's like, it's going to be pretty clear to you intuitively that the area under the curve of like the square of this is going to be, it's going to exist and it'll be finite. So the mean square sense convergence theorem is super general. Maybe I won't do this one since we're out of time, unless you want to see it in office hours, but you can also check 4.3.4. So take this Sturm-Liouville problem. Take this Sturm-Liouville problem and use an energy argument to show that the eigenvalues have to be non-negative. And you can either use the Rayleigh quotient if you can cite it and remember it, or you can just multiply both sides by y. That's where this comes from anyway. And the Rayleigh quotient. You see, you do this trick of multiplication by y and integrating. You can do one integration by parts to pick up those boundary values. And that's another way to look, to see that it's yy prime from 1 to pi. Plug in these conditions, see that it's 0, and you'll be able to argue that the lambda here has to be non-negative. Okay. Just went through that really fast, but just wanted to point it out. So what are you being asked for? Chapter 3, 4.1, 4.2, 4.3. You know those convergence theorems. classical Fourier series, Sturm-Liouville problem. This example problem, 4.2.4.13, it's kind of a monster, but I want you to be able to do a problem like that, not on the test, but be able to do a problem like that, and therefore, if I'm asking you a series of test questions about a problem like that, with things that you can write down with pencil and paper, then I want you to be, confident you can do that. And then we'll just stop talking about separation of variables because I'm kind of over it. So yeah, what's next on our plates? We'll see on Monday, but let's not muddy the waters talking about it right in the moment. So thank you everybody for your time and attention. We'll see you on Friday for that test. Have a good day.